Okay, so we come now to the fundamental theorem of calculus, part 1, or what most books would call the fundamental theorem of calculus, part 2. So, in order to show why we need a different part of the fundamental theorem of calculus, let me remind you of what the part we just did was called. The part that's called part 2 in this book, but I usually call part 1, never mind. The part that we just did says that if capital F is an antiderivative of lowercase f, then we can evaluate the definite integral from a to b of lowercase f by simply calculating capital F of b minus capital F of a. There's a sort of a deficiency in this part of the fundamental theorem of calculus. What is it? It comes in the form of this word, which is if. It says if capital F is an antiderivative of lowercase f, but we've never proven that there was such a thing as an antiderivative. So what fundamental theorem of calculus 2 does is, in this kind of roundabout way, shows that for any function that's continuous on the interval ab, there is an antiderivative. It doesn't really tell us how to find the antiderivative. It just sort of proves that there is one, so that we can then go and use the fundamental theorem of calculus with whatever antiderivative we can find by another method. So this is the statement of the fundamental theorem of calculus. It says, suppose that lowercase f is continuous on the interval closed ab, then define the function capital F of x in this rather strange way. Define it as the integral from a to x of f of t dt. So notice that the variable here is actually the upper limit of integration. Then what we can say is that f of x is continuous. The capital F of x, the function defined in this way, is continuous on the interval closed ab, and it's differentiable on open ab. And most importantly, its derivative, the derivative of capital F, is lowercase f. In other words, capital F is an antiderivative of lowercase f. I've put this in here not only because it's in the textbook, because this is often how you see it. Usually what we're doing is giving you this really, really ugly expression where we put d over dx in front of this integral and ask you to find the derivative. And it's kind of tricky because it's a remarkably simple derivative to find. You simply take the f of t that appears after the integral, you replace the t with x, and you're done. So let me just show you what's going on. In other words, let's focus on this function. What are we really doing here? Well, in sort of a simplified form, what we're doing is, let's suppose that I have this function, that this is y equals f of t, and suppose that I have t and y on the axes. In other words, I've just changed the name of the horizontal axis to t. There's no real significance to that. This is a t here. So what it means is that if I start, let's suppose that I have some fixed left boundary at x equals a, but I have, sorry, at t equals a rather, but I can move the right boundary arbitrarily far to the right. So what I'm really doing is I'm coming up with the signed area under the curve f of t on the interval from a up to some movable right boundary. So if you think about it, like, what that means is that if, let's say that that's a, and this is, let's call this 5. So I'm going to assume that a is less than 5. Then what that means is that f of 5 would be that area. On the other hand, if let's say that I made this 6, well, now we can add in a little bit more area. Let's add the green area. So now f of 6 would be the yellow plus the green area. So in other words, what this function is doing is it's just saying, let's find the area under the curve f on the interval that begins at a fixed point a but has some sort of movable boundary x. So I'm defining the amount of area just as a function of x, which is where I put the number, where I put the exact right boundary, where exactly I put the right boundary x. So that's what the fundamental theorem of calculus does. It basically says that this area function is an antiderivative of the function we're trying to integrate. It does this by constructing the function, and then, although we're not going to prove this theorem, the proof of the theorem basically shows that the derivative of this function is f. So that's what the first fundamental theorem of calculus is about. Now, okay, so how does the second fundamental theorem of calculus usually come up in a problem? Normally, the way that it comes up is by asking you is by presenting you with some horrible looking derivative of an integral and asking you to evaluate it. The point is to recognize that this is just a derivative rule for this very strangely defined function. So what I've done here is I've written evaluate d over dx of the integral from 1 million to x of sine to the 57th 1 over t to the fifth plus e to the square root of t dt. And you look at this and you go, oh, how am I ever going to use the chain rule and find things like the derivative of e to the root t and 1 over t to the fifth and sine to 57th? This looks absolutely terrible. How am I ever going to even find an antiderivative of this? And the whole point is that you don't have to, because we found that this integral is of the form integral from a to x, where a can be any constant, including a million, of f of t dt, because that's what this expression is, where, of course, this horrible looking function is f of t. That means that the answer is simply having recognized that that's the form of this integral. The answer is simply sine to the 57th 1 over x to the fifth plus e to the root x, and that's it. Now, what would be some wrong answers that I see here? First of all, wrong answers would look something like this. Here is some wrong answers. Some people will try to find an antiderivative of this function, and of course, since we're not really in a position to do that, usually it gets done incorrectly. So, for example, a wrong answer might be sine to the 58 1 over x to the fifth plus e to the root x over 58 from 1 million. Actually, these would be t's in a properly done wrong answer. 1 million up to x, and then people would try to substitute in substitute in the x and the 1 million. So that would be one example of wrong. People just sort of pre-program to say, oh, anytime I see this integral sign, I have to find an antiderivative. And the answer is no. This is an example of a problem where you're not finding an antiderivative. So then the next type of wrong answer that we often see. So the next type of wrong answer that we often see is we'll see someone who basically get it right and say something like sine to the 57th 1 over x to the fifth plus e to the root x plus c. Once again, there are a certain number of students who just never make any effort to understand what the plus c represents and just sort of assume that any time their mind processes a symbol that looks like this, somehow the answer should have to have a plus c in it. But of course it doesn't, because we're not finding an indefinite integral. We're not finding a general class of antiderivatives. We're not finding any antiderivative, in fact. So the plus c is just wrong. So that's so those are some wrong answers, some things that you don't want to do. This is really just a remarkably simple problem to do once you recognize what's being asked of you. The whole point of it is the recognition. You have to forget the association between seeing this shape and finding an antiderivative, and understand that what you're being asked to do is find the derivative of a function that's defined in a fairly strange way. So, okay. Let's